では、早速ですが、第3位のエクストリームエッジ賞を受賞しましたチームマシンラーニング東京 MLT さんのプレゼンからお願いしたいと思います。
Thank you, Obuchi-san. Okay, let me share my screen.
Yes, I can see
Okay.
you.
Yeah, thank you for the confirmation. Yeah, hello all, good afternoon. So we are from the MLT Edge AI team. Let me introduce what MLT team is about in a few words. Machine Learning Tokyo is dedicated to democratizing machine learning through 3 O's. First is open education, where we conduct almost 200 workshops and study sessions as of now. The second is open source, where we actually actively work on open source and open sourcing the community efforts. We have about 5,200 total stars on GitHub. The third one is open science, where we try to publish papers from the MLT community. Here is the MLT Edge AI team introduction. Alisher, he is a co-director of MLT. He is also a machine learning engineer and a computer vision researcher. He is pursuing his PhD at the University of Tsukuba. Ben is an engineer working with drones, robots, and really interested in Edge AI. Hajime Kato is a software engineer at Rakuten. He is interested in competitive programming, computer vision, algorithms, and like maths. We have Naveen. Naveen is a senior technical scientist at Riken. He is an Edge AI expert and likes to experiment with latest Edge hardware boards. And finally, myself, I am Yuvraj, co-founder of MLT, and I like to work on Edge AI and hardware projects. I also work in Rakuten, and I'm leading a team of small ML engineers, a small team of engineers. So this is the today's agenda for the presentation. Okay, so as Hamanu-san had mentioned previously, this is the problem statement of the context. I won't go through it again. Here is the MLT solution for the competition. It's a two-stage solution. The first stage is object detection using RetinaNet. We use batch augmentation techniques to process the frames before feeding into the object detection block. The second stage is object tracking using the Hungarian algorithm. We use position, speed, visual features to track the objects. From timeline perspective, we had only 2 months till the deadline. So we started to work on this project in May. We worked every weekends, mostly on Saturdays and Sundays, and had a sync up meeting on Sunday to discuss if any blockers are there or in order to share the progress. As we entered June and the deadline neared, we had to meet after office hours to push the team to submit better model. And the results of it, of the efforts, were like we got the third place. Thanks for the entire team. So here I would like to go into some EDA work which we did on the video data. We did some exploratory data analysis on the video data to take help of the heuristics to select the detector and tune the tracker. We analyzed the object size in terms of area, number of objects to track per frame, and also the brightness of the image throughout the video. The EDA work helped us to select some heuristics for the model. We use the Keras RetinaNet framework with ResNet 101 backbone as our model. Of the 7 classes, we use 5 classes for training our model, even though the evaluation will be done only on 2 classes. The reason was to enable model to understand what is not a car or not a pedestrian class. For example, to differentiate a car from a bus. For the input data, we did not resize the image as you see in the video. The pedestrian objects are already so small, so we might lose that information on scaling down. We use a logical reasoning for selecting the augmentation methods instead of using random augmentations. For example, if I go through them quickly, the rotation and the shearing augmentation. The reason to use this augmentation was because a car takes a left turn or a right turn, and the objects in the frame experience this rotation. The translation augmentation was used because the objects move from one frame to another. For the scaling augmentation, the same class objects might not have the same size. They vary in different size in the same frame. For the horizontal flip augmentation, it helped us to detect objects in a better way using the mirror images. And the contrast augmentation, this was quite also important because the brightness varies. For example, when the car goes under the tunnel. So these kind of augmentations we selected and then use it to train the model. And here are the average precisions which we got on the model. The next part is object tracking. Object tracking was developed by Kato-san. Object tracking model uses bounding boxes generated by the object detection module. The goal of the tracking is to assign same ID to the same object throughout the video. Here is the visualized output of the tracking module. Here the same color means the same object. The slide explains some important patterns and reasons for selecting Hungarian algorithm. The pedestrian in the black dress in the first frame is not visible in the second frame due to the car. The pedestrian in which the white dress person goes out of the boundary in the third frame. We want to match boxes to differentiate them by a score based on the close position and the similar size and the similar image. So this is nothing but a maximum weighted matching, and we used a Hungarian algorithm to solve this. As mentioned in the previous slides, we need a score to match the boxes based on the box distance and the image similarity. For box distance, we first predict the next position of the box by using a quadratic regression and then compare it with the actual box using centroid distance. For image similarity, we resize the two images to the same size, crop to the center part to remove the background, and blur them to suppress the noise. Then we can calculate the HSV histogram and use the correlation matrix to compare the image similarity score. To optimize the model, we optimize this model for the ground truth data first and then fine tune the model to match the prediction data. We got an error ID mismatch rate of about 1.5% for the ground truth. Okay, so after combining the object detection and object tracking modules together, we did a dummy test run and a dummy submission to test the entire pipeline. It took some time for integration and submission, which we could have saved earlier. As you know, like time becomes so precious when we near the deadline. So we first figured out the different parameters for the model which we want to fine tune. For example, in the left side here, you see left or right flipped image, then the contrast adjusted image, NMS threshold for the car and pedestrians. Then we populated all the different patterns by deciding on the range of the values for the parameters. The Excel sheet snapshot here shows the list of different experiments designed for the multiple patterns. In total, we did about 40 different experiments. We assigned them among ourselves to speed up the evaluation of the model. While the model score gave us the quantitative judgment on the model, we missed the qualitative judgment. So we overlaid the model output on the original videos to watch the videos throughout the entire video to understand where the model is performing or to understand the points of improvement. So in this picture here, the black box is a ground truth and the colored box is the object detection output. We visualize object tracking by using the color of the box. So the same color is same object ID, and if the color changes, the color of the box changes. Let me share some conclusion from this project. The test was separated on public and private set. So never train too much on the public test set, as your model might overfit the data. This can lead to surprise changes in rank before and after the competition, as we saw during the competition. We had sufficient resources to test time augmentation, and it helped us to improve the model. We use different non-maximum separation threshold for different classes. Data exploration is very important. Ben helped us to develop these heuristics for the model and test to understand the heuristics for the model. Also, it's quite important to assign someone to keep track of all the non-technical part, like for example, weekly meeting, next steps, progress tests, etc. While doing multiple experiments, there might be different scores achieved in different experiments, but it is quite important to find the critical improvements which made the score to change. So this needs to be documented properly. Lastly, but not least, do not underrate any idea when working in a team. Be open to every idea and spend some time to think about it. This is the reason we say this is because previously we thought like we would use a re-identification method, but we didn't had much time to test it. Okay, so after completion of the competition, we wanted to go one step further and deploy this on edge hardware. So we faced many problems when doing this. So we divided our problems into 4 quadrants, which we think are the prerequisites for deploying on the edge. Naveen worked on the model deployment and model optimization for the edge, and Ben worked on the physical deployment and product part. Let me quickly go through each of the quadrants briefly. Naveen started experimenting to deploy the model as it is on different boards. The table shows the results of experiments. For Jetson Nano, we didn't have much issue apart from few optimizations. The model runs as it is on Jetson Nano. For Raspberry Pi, the model needs to be converted to OpenVINO representation. Performance-wise, it is almost similar to Jetson Nano. For RockPi, it failed due to special operations, ops, which were used by RetinaNet. Right now, RockPi does provide a compiler, but we couldn't get the compiler to convert the model. And for Google Coral or Asus Tinker Edge, we are still facing some issues around TensorFlow Lite. I hope so that will be fixed in the future versions of the TensorFlow. So we decided to use Jetson Nano for our edge device. And here are the changes which we faced when we did transition from Cynet environment to Jetson Nano environment. One main challenge for us was the model memory and the inference time. As you see, memory size got scaled down by 4 times, while the performance dropped by 50%. Edge devices are low power devices. For example, in Jetson Nano case, it is 5 watt or a 10 watt power. So optimizations are very critical to be able to run your model on the edge. Also, software optimizations are equally important. For example, when it comes to using libraries, it's better to use natively compiled libraries. Another optimization is the is the environment optimization. So running Jetson Nano with a GUI itself consumes a considerable chunk of GPU memory, which caps the memory for the model use. So we thought we would better disable the GUI and just use the CUI mode of Jetson Nano. Another optimization from the model perspective is to convert it to TensorRT, but unfortunately, due to unsupported ops, we couldn't convert it yet. Then we use the Jetson Nano with the 10. This is the field testing which we did. So since we finished the competition, we had some time. We thought we would go to a field testing and actually deploy it on a real device. So we use Jetson Nano with a 10 watt mode. For power, we use the 35 3S LiPo batteries, not 35, sorry, 3S LiPo batteries, which provides the output of about 5 volt and 3 ampere. With this particular power, we could run the Jetson Nano for about 2 hours. We used a USB camera and a Wi-Fi access point. The Wi-Fi access point was particularly helpful for us to debug and SSH into the Jetson Nano when we were on the field. For 3D printing idea, we wanted to use this model for the real life application. So we came up with the bike idea to fit our model on a bicycle. We designed and 3D printed the case in order to be able to fit the model on the bicycle. I think we were able to learn other engineering skills too, apart from the software engineering skills. One important learning point we want to focus on is not just deploy to deploy, but deploy with an application in mind. That is what our main focus was. These are the results of our model running on Jetson Nano on a bicycle. One surprising find was that the model performed well, even if the blurry image due to bike vibration was fed to the model. Another find was that legs were detected as pedestrians. We think it might be because the model environment changed from running on a highway to running on a pedestrian road or a footpath. With that presentation, we would like to share MLT Edge AI Labs' next interest. We are interested in working more on these kind of like Edge AI technologies in future. If you have any questions or queries, you can ask it on the Zoom chat, or also if time doesn't permit, you can always check our MLT Slack channel, and it's open to everyone. Also, finally, I would like to thank for providing the opportunity. First, I would like to thank Cynet for providing this kind of, for hosting this competition. I would also like to, I think it helped us to work together and understand the challenges in the field of Edge AI. Also, I would like to thank METI and NEDO to take these initiatives to support the Edge AI competitions. It is very inspiring for all the researchers and engineers to be able to have support of such big organizations. And lastly, but not the least, I would like to extend my thanks to MLT community as well to provide support for working together in a team. So if we have time, I don't know if we have time, but I would like to show a field testing video, which we just as a fun video, we captured it while doing the field testing. So if you don't mind, I would like to just share this video. Yeah, this is like actually getting the bicycle and then mounting things on it. We experimented this around the Tamagawa, Tamagawa River.
Hello. Okay, let's
We had to practice social distancing because of Corona, but yeah, we try to make sure we follow.
Hey guys, what are you doing? Hello.
For the hardware implementation, as I mentioned, we use the basket of the bicycle in order to mount our Jetson Nano and the camera. So here you see the Jetson Nano directly rests inside the basket, and we have connected these batteries together to power the Jetson Nano. The two antennas are the Wi-Fi access point, and then there is this camera connected to the front of the basket. Yeah. And so while running test, we actually tried to see, like we had two cycles. So one from behind, we tried to take the video of the person. This is Naveen. He's trying to run it as slow as possible so that we can capture the frame rates properly. We also saw like if it was too fast, we couldn't capture all the frames, and it missed some predictions. It was quite fun. I think this competition helped us not only to improve our skills, but also this kind of like real field experience was really fun for us. Thank you, everyone. I think that's it from my side, from MLT side. Thank you.
Thank you for your presentation. So we have got two questions from the audience, and also if you have any question, please raise your hand by clicking the hand button, and I will turn on the your voice. So anyway, let me start from the first question. And so you don't use the resize image. With the resizing, how to predict the image with the high speed? Do you have any technique know-how for this?
For resizing image with high speed, right?
Right. No, you might not use the resizing, so.
Yeah. So I think so traditionally I think there is this default resize function which is present in OpenCV, right? So if you use that, I think it is too costly or too performance. It uses a lot of resources, and maybe Alisha can also help me to answer this question. But I remember we, instead of using that function, we sometimes like did a pure matrix operation by ourselves in order to optimize the performance. So that kind of small tricks are very important when it comes to performance. So instead of for resizing or for changing it to gray format or doing this image processing operations, writing them directly as matrix operations.
Okay. So second question is, what is your technique to predict a small image with a high IOU?
Small image with a high IOU. Alicia, do you want to take this?
So I think there is a distribution. One distribution case is presented by Hamano-san in the previous presentation. And if we have smaller images, but still we got the higher IOU. So do you have any observation about this point? So we have the many pedestrian is a small image sizes, small IOU, but still we might got the higher accuracy.
Yeah. For that part, actually, I think the scaling part with the augmentation part helped us to focus on that particular area. And this augmentation is we use not only for the training but also for the test purpose. So I think those small, especially I guess the topic is about this small pedestrians, right? Like where you have small boxes with a high IOU. So those kind of objects, I think we try to use the augmentation part during that in that section, in that area, around that area.
Okay. Yep. So do you have any other question, comment? Okay, thank you very much.
Thank you everyone.